on Tuesday, we spoke about k-means and then about EM. Two classic algorithms. K-means is 100 years old, EM 70 years old. We're now making our way to 40 years, 50 years old, 20 years old, and then next Tuesday we'll be at 5 years old. The idea behind these fancy mathematical ideas that I have had to compress in these difficult equations is on the high level that inducing structure in a probabilistic model can be used to create algorithmic efficiency, to construct programming structures in your code that allow much faster convergence of much more expressive models. So the first instance of this, from 100 years ago, Hugo Steinhaus, is k-means, which I had up there. This is what I spoke about on Tuesday. It's an algorithm to fit a mixture model, specifically a Gaussian mixture model, where the Gaussian clusters have no covariance or standard unit covariance, but just a mean that gets fitted. And we found that this algorithm, which has an iterative structure, alternating between assigning points to clusters and then fitting clusters to the points assigned to them, and then repeating, that amounts to maximizing a log likelihood of such a Gaussian mixture model. Actually maximizing the log likelihood of the parameters of the model, which are the assignment of points to clusters and the parameters of the clusters. In the case of k-means, by the way, this log probability for the data given the clusters is just a Gaussian with a mean and a standard unit covariance, but this could be something else as well for other data types. And then we made a step and said, oh, actually, there's a refinement of this algorithm that doesn't maximize the complete data log likelihood, so the likelihood involving both theta and z, but it maximizes the expected complete data log likelihood, and that's called the EM algorithm. So we maximize this expression, but under an expectation over the latent quantity. And then it turned out that the right thing to take the expectation over is the posterior distribution over z, because then at the time when we set this distribution, this posterior to the posterior at theta hat, and then optimize with respect to this theta, we're actually closing the gap between a lower bound on the thing we're trying to maximize, the log evidence for x given the parameters, having marginalized over z, and the so-called elbow, the evidence lower bound, which is actually this expression here on the left. And then because we close this gap and then raise it, we are guaranteed to increase the marginal log likelihood of the model in every step, and then therefore get a good model in the end. So that is an algorithm. So this, I introduced it as having been invented by Hermann Otto Hartley and Dempster and others in the 50s. What I want to talk about today is the direct continuation of this idea, in statistics at least, throughout the second half of the 20th century. And what I want to highlight is also its sort of story of how it influenced the development of the nascent field that we now call machine learning. So to do that, let me briefly remind you of how the EM algorithm worked. So our goal is, someone has given us a model. This model involves a probability for some observations. Given some parameters, we'd like to know what good parameters are for this model. We want to do maximum likelihood inference. So to do that, we invent some new variables called latent variables, z, that we think somehow simplifies the computation. And there is usually some ingenuity involved in coming up with those. Then that means we want to maximize this expression. This is called the complete data log likelihood, because there's now this new object that we've invented. And the way we're going to do this is that we first compute a posterior over these latent variables. Hopefully we've chosen them such that we can actually do that. Then, given a particular current estimate for the parameters theta, we set a current estimate for the distribution over z as the posterior given those parameters. That means that when we look at this object called the evidence lower bound, we are effectively making this a tight lower bound on this by setting the KL divergence between our approximation and this particular posterior to 0. And then we raise this expression as a function of theta, but only this theta, so the theta in Q is kept constant. And that's often possible analytically, and then we're guaranteed to raise the marginal likelihood. The first thing I want to point out is that I set maximum likelihood inference, and this is a probabilistic learning course, so you probably should think, but shouldn't we do posterior rather than likelihood, because likelihoods can be dangerous. That's completely true. It might be better to do this in a posterior sense rather than in a likelihood sense, but actually doing that is really straightforward. So if you want to do maximum a posteriori inference rather than maximum likelihood inference, the only thing you need to change on this slide even is just this red bit. So you just add a prior for the parameters theta, then you're effectively maximizing a posterior rather than a likelihood. And doing this is very easy because you can see that this theta does not show up in here. So this integral is actually just, I mean, if you think about what we add here, then there's just a term plus integral over q of z p theta dz. P theta doesn't depend on z, so the integral commutes out. We just have a log p of theta times integral over q of z, which is 1, so just log p of theta. So we just add a regularizer basically to the optimization. Then you keep this running until it converges. Now you have a maximum a posteriori estimate. And I motivated all of this with this sad story about brilliant mathematicians in, Central Eastern Europe in the 1930s. And actually, the path of these people now leads us, as science tends to be, because science tends to actually happen in very small communities, to across time and space to a different place where the mathematical story of the idea actually continues. So this is a picture from a colloquium, so today we would say like a weekly talk, at the Los Alamos laboratory during the Manhattan Project in 1946. So the Second World War had already ended. The nuclear bomb on Hiroshima and Nagasaki had already been dropped. And you see here in the front row, I actually made some notes, so I'm not going to tell you anything wrong. In the first row, Norris Bradbury, he was the director of Los Alamos. This person you probably don't know. This is a Nobel laureate, Enrico Fermi. He's probably the father of the nuclear bomb as such. Does anyone recognize anyone else in the picture? Maybe the guy with the black jacket? Yes? Yes, this is J. Robert Oppenheimer, now Hollywood famous. In this picture, he's 42 years old, clearly still a young man. And they are actually watching a talk on what they called the super bomb. Now we call them H-bombs, hydrogen fusion bombs. The talk is probably given by Edward Teller, who was also an emigre from Europe. He studied he was Hungarian, studied in Germany, emigrated. He was Jewish. He had to emigrate in 1934, having just finished his degree with his wife, Mitzi Teller. And then he got to work quickly at Los Alamos and sort of had this crazy idea that it should be possible to build a fusion bomb. He worked on this together with a colleague who we remember and met already in Lviv or Lwów or Lemberg last lecture, Stanislav Ulam, who was a part of the Scottish Café. They together did computations using early Monte Carlo methods, for which Mitzi Teller also invented some part of the algorithm, essentially Metropolis Hastings, but they did the computations with an analog computer called the ENIAC. It was like a little machine that you had to move around on a drawing to simulate the path of particles being scattered inside of a geometry of a nuclear bomb. They tried to find the geometry such that fusion would ignite, and they would get a very high concentration of particles. So there is Monte Carlo methods being used, for impact, let's say, because they created, overall, this was the outcome of all of this. But in this picture, so this was the very first hydrogen bomb shot. This is Ivy Mike. In this picture, there's another person a young guy, a group leader, today we would say an independent group leader at one of our institutions, right next to Oppenheimer. Does anyone guess who this is? It's Richard Feynman, later Nobel laureate. And he made his name with work on what we now call variational inference, in physics though. He already gave, at this point, he's 28 years old, he already has his PhD, he's basically a postdoc. He just gave a talk recently, like a few years ago, to people like Albert Einstein and John von Neumann, who were quite intrigued by his work. He was supposed to be an absolutely brilliant theorist. And he's extending work that was introduced as under the name of the calculus of variations by various, well, old mathematicians from a long time ago. So some names associated with this are also Isaac Newton, very early version. Then Leonhard Euler got interested, but Lagrange actually provided the first formal definition of this idea of the so-called calculus of variations that Euler then directly took over. The idea of the calculus of variations, very vaguely spoken, without showing you any math, but we'll go into the math quickly enough, is that just like we can do derivatives on functions and then follow derivatives and gradients in multivariate calculus to find modes of functions, right? So to maximize the value of a function, it should also be possible to construct the equivalent of a derivative in spaces of functions, rather than in real-valued vector spaces, in spaces of functions, to maximize, what is the corresponding concept? To maximize a functional, so a function of a function. And for that, we need something like a derivative in function space that we can then follow to maximize such a functional, an expression. And Lagrange was like totally excited about this idea, and Feynman got excited about it as well, because it was a crucial ingredient for the theory he was working on, quantum field theory, where the expressions you want to maximize for are functionals of incoming probability distributions over particles. There is, by the way, just before we move on, just to not leave it out, also a corresponding equivalent to, well, sort of the idea that you also know from Lagrange multipliers, so finding directions along which a functional is invariant. Right? So just as you can follow a gradient to find a mode, you can also think about spaces identified by zero gradient, which are equipotential lines. So spaces along which something is invariant and does not change. This is called the theory of invariances in variations, and it's associated with the work of Emmy Noether, who was probably the most famous mathematician of all times, which also made major contributions to physics, identifying conservation laws rather than optimal choices. But today we're going to focus on the optimization problem, on the idea of how to maximize a functional. Our elbow is such a functional. It takes in a distribution Q, right? That's a function of Z. And then we want to find the function Q, which makes this expression maximal. So this expression is clear. Oh, I forgot the differential. So it's a derivative integral over dz, right? So it's something that takes in the input over z and marginalizes it out, integrates over it. And now we have a number, or actually we have a function of x that we can try to maximize for a particular x. So what does that mean? So this is the physics motivation. I'll talk more about that in a second. Where does this what does this come in? What does this have to do with machine learning? What does this have to do with inference and approximation? Well, machine learning is the continuation of physics into everything else. It's the application of mechanisms from science into every other aspect of human activity. That's maybe why it's so exciting and why it's so influential at the moment. So let me try and generalize the ideas both from the previous lecture and from this physics background in a few slides. So and for a moment, let me try to be more concrete. So let's say we're trying to do inference in a model that assigns probability to some data points x. So x is the things we get to see. And our model will involve some parameters theta, and it'll involve some latent quantities, which we need to describe what's going on. We could think of them as nuisance variables, or maybe we think of them as the things we're particularly interested in, the variables of the model Z. So in the algorithms we've encountered so far, in k-means and EM, we had to make very specific choices for Z. So the name of the game was, let's find the right latent variables such that this posterior over Z given x becomes tractable, and we can just write it out for a particular value of theta. When we can do that, then our elbow, then we need two things actually. We need to be able to get the posterior tractable, so we need to be able to evaluate this function, not just to evaluate it, it has to have a closed form, and then in addition, we need to be able to compute this quantity, where q is now set to p. So let me go back up. Why did we do it? Well, I mean, yeah. So we need to plug for q, we need to plug in this posterior, and then be able to do this integral. Then we can do EM. But maybe we can't do that integral, or we can't evaluate this posterior. That seems like a strong constraint, and makes EM a sort of a very specific tool that you can only apply when you can do when you actually can compute the posterior and the associated integral for the elbow. Maybe sometimes we can get away with just saying somehow we'll allow q to be something more restricted, something that some space of functions in which we can do tractable computations. And then we just maximize this elbow, this evidence lower bound, within the space of things in which we can do this, within the space of probability distributions q in which we can compute. And when we do that, we'll then find some q that minimizes KL divergence, right? Because raising the evidence lower bound means we get closer to the evidence. And as we do that, we narrow the gap. The gap is given by the KL divergence between our q and the posterior over Z given x. And then this q that we find within the space of tractable distributions will be the best possible tractable approximation to the posterior that we might want to have. And that's actually the entire idea. So this is an optimization process within some space of probability distributions, Q, and that idea is called variational inference. Well, because variational is the word for optimization or sort of the generalization of derivatives to function spaces. And of course, that raises the question of what do I mean by a space of tractable distributions? I'll tell you in a second. Because it's actually surprisingly fluid, this definition of tractable. But before I do that, let me first make the connection to physics, because I said that's all associated with people like Feynman and so on, so that you understand why people might be interested in that. And actually also to make my case that machine learning is just a continuation of physics to everything else. So here's how this works in physics. So these problems show up in what's called statistical mechanics or thermodynamics. So this is the study of systems that involve many, many, many particles, a large set of particles or large set of things that all have their degrees of freedom. Let's say their degrees of freedom are x and z, whatever this is. It's like the position, the momentum of all the particles in a gas, the spin in some quantum gas, and so on. These are called the microstate of a system. So it's the set of parameters or variables that describe everything. But we assume that there's many of them, like 10 to the 23, right? So a very, very large number of them, and therefore we can't actually see them. But we can write down how energy arises in this system. In principle, it's just too many numbers to track. So we write down an energy function, a total energy, E, that's just a function of x and z. And then that energy, as you now know already, is associated with some probability distribution. So particles just take a configuration according to e to the minus energy. That's actually sort of a circular statement. The energy is basically this, right? So the energy is the logarithm of the negative logarithm of the probability. So the typical challenge now in the theory, like the statistical theory of mechanics or thermodynamics, is that you can't actually go in and measure the state of every single particle or every single element of your system because it's large. There's like 10 to the 23 molecules and they all behave in a very complicated way. What you can measure though is what's called macro states. So you can measure the temperature, you can measure the pressure, maybe you can measure some chemical potential, something like this. These are called macro states. And the way you usually measure those is by taking the system and letting it do something. You're letting it expand to measure its temperature or its pressure. You measure the force it exerts onto walls to measure pressure, something like this. And so this means you're using some energy that's available in the system to measure the macro state in a very abstract fashion. And that's why the quantities that we tend to measure in terms of macro states are associated with something called the free energy. So free energy is really just a word that physicists and chemists actually use to describe properties of a microscopic system, of a statistical system that one can use to do work. And that allows us to now separate the x's and the z's, basically, right? So sort of in a sort of backward definition, we could think of the variables x in our model as the things that the aspects of the system that we get to measure as a function of, that we get to measure a function of when we measure macro states, like temperature, or pressure, or some work that the system can do. And the z's are the other variables that somehow only indirectly affect the macro states. And so we can define something called the free energy as the negative logarithm of a marginal over our probability distribution under Z. So it's the negative logarithm of the distribution of x. And so x might actually be a very small set of variables, and z might be a huge remaining set of variables. And they're actually now, well, okay, so I'll talk about free energy in a second again. So what you now might want to do is you might want to figure out what the remaining degrees of freedom are, what the z's are that you may still be interested in for some reason, but you can't measure them directly. So you're going to find some probability distribution that approximates the correct posterior on Z, the conditional you would get under all of the observations by fitting some parameters of a model. And that involves writing down something that in variational theory of physics is called variational free energy. And that happens to be exactly the negative of our elbow, because you're minimizing it. So then what the physicist does is they try to find an expression that minimizes variational free energy, which is the same as maximizing the elbow. So they're effectively doing approximate inference to find an approximation to the posterior on the distribution over some interesting latent quantities of a system that can't be directly measured through workable energy, through free energy. And then a large part of the game in thermodynamics is that people have come up with various different ideas for free energy. And there's all these different words that if you've taken a thermodynamics class or a statistical physics class, you've encountered, like the Helmholtz free energy or the Gibbs free energy. And they're associated with these people. So Rudolf Clausius was a German physicist who coined the term entropy first. It came from him. He was looking for a word that sounded a bit like energy, because he was thinking about the ability of a system, the differential of a heat in a system that can be used to return heat back and do work with it. He initially wanted to call it the Verwandlungsenergie, but that was a weird word that nobody understood. So he was looking for a Greek word because he thought ancient languages survive for everyone, and everyone uses the same ancient languages, at least in the Western world in 18-something. So he came up with entropy, which is the Greek word for transformation, basically, so Verwandlungsenergie. And as a contemporary said that he succeeded in finding a word that meant the same for everyone, namely nothing. And let's be honest, to this day, nobody really knows what entropy actually is. beyond an expectation of a logarithm. Then Helmholtz was the first maybe to come up with this idea of free energy. He defined a certain type of free energy that involves entropy of a system, and it's all about what kind of work the system can do and how you measure it. Then Josiah Gibbs, also a very influential English physicist in thermodynamics, had a new way of expanding the idea of free energy. So he added an extra term to it, that's pressure times volume. He calls this U, by the way, is the potential energy plus pressure times volume. He calls this the enthalpy. Somehow funny that they all came up with something similar to energy, right? Entropy, energy, enthalpy. And then I'll do a jump, just to connect the dots, to a contemporary colleague, Dave Bly, from Columbia University now in New York. And to my knowledge, he was the first to come up with the word elbow for evidence lower bound, yet another word with an E. And he's a statistician, or machine learner, we would say these days. He really phrased this very clearly as the variational energy being the negative of a lower bound on the evidence in a general statistical model that we can apply way beyond physics and maximize. He also came up with some early, very structured algorithms for language modeling long before large language models. So how does this optimization in the space of functions actually work? So it's going to work in the following. I now have several slides that try to explain in as directly as I managed to, because it's actually quite challenging, how this idea of optimizing for a functional for a function might actually work in practice. And you can maybe imagine that this is going to be hard. Why? Because, well, for functions over a vector space, we know how to compute gradients, and then the gradients are vectors in the vector space. So these vectors are tractable objects, right? They're just a bunch of numbers that you can follow. You can write out an algorithm that just follows a gradient. But if you think about a functional that takes in a function, so a functional is an integral, and we need to optimize this with respect to a function. Functions are infinite dimensional objects. So we can't expect that we're going to compute some infinitely long vector that we can somehow follow on a computer, right? So the process is not going to be that we will compute a derivative in function space and then do a few steps to optimize the values of the function. That doesn't work. And instead, we're going to find implicit statements that characterize a mode in the space of functions. And then those implicit statements will surprisingly sometimes actually tell us what the optimal function is. So this is how this is going to work. We start again with our model. We invent some latent variable z. X are actually given data, and we have some parameters theta. We want to find a good approximation to the posterior over the latent variable z, given x. If you have a model, then the posterior is well defined. It exists, but it might be intractable. We might not be able to write it down. So what we're now going to do is we invent some family of distributions Q of z. And then, well, that's a stupid sentence. Why did I add this there? No, that's not actually what I want to write. Well, this might be, again, one of the things that I fixed. Let me just do this. Well, yeah, or maybe it's just confusing, and that's what I wanted to write initially. But let's actually keep it simpler and just write it like this. So we invent some family of distributions Q of z, and then we want to optimize the elbow, which is this thing as a function of, as a functional of Q of z. I mean, so Q of z might well depend on our parameters, sure, but the goal will be to find a Q, a function of z, that maximizes this expression. And this expression is an expectation over this function under Q of z. So it's an integral that gets rid of z, basically. So here it is again. When we do that, if we manage to do that somehow, we don't yet know how, we're going to minimize KL divergence to the true posterior. So what we find will be a good approximation in the sense of this divergence. So if we believe that KL divergence is a good measure of distance in the space of probability distributions, then this process will find the best approximation to the posterior within the space of Q's that we consider. Now, if we don't expect any, if we don't impose any restrictions on Q, if we just say within the space of all probability distributions, find the optimal Q, we know what the extremum is going to be, the optimal value. It's going to be this probability distribution, the posterior. But we know that we can't compute that, or we assume that this is not tractable, because if it were, we would just compute it. So we'll probably have to somehow restrict the family of distributions that we want to consider. And you might think that this restriction will be something like, oh, we're just going to assume that they're all Gaussian or something like that. And that's actually an option. But it turns out that sometimes you can be much more subtle. You can impose very weak restrictions on the space of functions that aren't even of a parametric form. And you still get an actual tractable distribution out. And I'll show you how this works after the break. But first, there was a question. Was it done? Yes. So we are not. So this is the thing. Like, let me just make sure you're not getting confused. We're not yet going to assume that that Q of Z will be a parametric family of distributions. It doesn't have to be an exponential family even. It could, in principle, just be anything for the moment. So the restrictions we are going to put in will be something very subtle. It will not be, oh, it's a Gaussian with a known variance, and we just have to optimize for the mean. That's actually also something we can do. This is sometimes called fixed form variational inference. And I'm thinking that I might introduce it at the beginning of the next lecture, also in another historical anecdote. But yeah, so like for now, let's actually keep it at that. So if there are no more questions, then let's take our customary 5 minutes. There was a good question during the break, which was also maybe triggered by my mistake of like the spelling mistake here or writing mistake here on the slide. Namely, what about this theta? So on Tuesday, we spoke about optimizing the elbow for theta. And that's at the heart of the EM algorithm. In EM, this maximization of the elbow in terms of the distribution Q of Z sort of happens almost implicitly, right? We just set Q of Z to the correct posterior because we can track the full posterior. And then we optimize in theta. So in the setting that we're now discussing, we can still optimize for theta. That's still fine. But this is not actually what I'm talking about right now. So what we're now considering is this sort of maybe like to make this aspect of finding a good distribution over Z an explicit part of the thought process. In EM, finding the best approximation Q is straightforward. It's just P of Z given theta. P of Z given X and theta, the true posterior. But we're now saying, well, what if we can't track the full posterior? What is another thing we could find? So we're looking for a function of Z. That function of Z might still also be a function of theta, and then we can also optimize for theta, fine, but it's just not important for now, right? So we'll keep those parameters like out for a moment and care about this thing as a function of Z. And we're looking for the best possible function of Z. And we know that the one best possible function of Z is the posterior of Z given X. That's the thing we'd like to compute because we want to do Bayesian inference, right? But let's just say this is not something we can write down. It's just too complex. I'll come back to the example of Gaussian mixture models later on in a few minutes, and then we'll see that there might be generalizations of that model where this Q of Z given X is intractable. And now I said this ominous vague thing is that we're somehow going to put some restrictions on the space of functions, probability distributions Q of Z. And again, it might seem like we would have to put some parametric descriptions. We'd like to say we are going to write this function in terms of a finite number of features. But actually, just like in the Gaussian process world, we got away sometimes without actually imposing a functional form on the space of functions, but instead using some kernel function. We're now going to get away without imposing a functional form, but by imposing a factorization. So a factorization is a statement like the one in the first row above. It says, so we're looking for this probability distribution over these latent variable set. So of these sets, let's say there is like 100, right? Or I don't know, n of them. And what we're going to, I have a weird clicker problem. And what we're going to do is we're going to impose that Q of Z factorizes into a bunch of terms that depend on, well, let's say some subsets of Z. So the Zi might still be multivariate subsets, or they might just be individual scalar variables. It doesn't really matter, actually. It's just some new variables, some subpart of this entire set of variables Zi. And you know that factorization amounts to independence assumptions, right? So maybe by imposing independence under our approximation to the posterior, so our Q is an approximation to P of Z given X, maybe the computation becomes tractable. And we're not going to impose anything else. We won't say what the functional form of Q is, just that it has to have a product over the Zi. So then what happens is the following. So let's look at our variational bound, our elbow that we're trying to maximize. I'm going to put it in its definition. So that's the full definition. But now I've plugged in the fact that we assume that Q of Z factorizes. So in our variational bound, remember that the variational bound is an expectation over Q over log of joint over Q, right? Log of P of X and Z divided by Q of Z. So if you take the logarithm, we can take this into a difference. And now we impose the fact that Q factorizes. So we have a product here and a sum here. And now we're going to do a thing, namely that we're going to pick out one particular set of variables, Zj. So there's this product over all the Zi. We're going to pick one of those. Let's call that Zj. I've actually highlighted this in this slide in red, but I realize now that you can barely see the red, right? So this Zj is going to be, for a moment, the thing we focus on. And then, of course, what's going to happen on the computer is we're going to iterate over the j's, right? We're going to do this for one j and then for all the other ones. So if we do that, then we pick out this one term from the product. And then in here, let's sort of move the rest of the terms of the product into a set of brackets. And then this joint integral over all the z's will be an outer integral over Zj, and then all the inner integrals over all the Zi's. Minus, over here, we'll get one particular term, because here's a sum over the Qi Zi, right? So in one of those terms, Zj is in there. So we'll get an integral over Q of Zj log Q of Zj. That's the entropy of our distribution Q of Zj, or partial distribution, or marginal over Q of Zj, plus something I'll call a constant. So why is that a constant? Well, because it involves the sum over the logarithm of Q of I Zi when you integrate out all the Zi's that aren't j. And then there's an integral over Q of Zj, which is just a 1. And so it's just a number that doesn't depend on Zj. Okay. Because we want to optimize for Q of Zj, that number doesn't matter. So now we're going to look at this expression, and we realize that it's sort of in a functional form. We have marginalized out the Zi. We've taken integrals over Zi, all the i's that aren't j. So what we're left with here, if you think of this as a function, then it's a function of x and of Zj, because all the other Zi not j have been absorbed. They've all been integrated out. So we're left with a function that we can think of as the logarithm of an unnormalized probability distribution over x and just Zj. So it's a function of only Zj and not the other variables. Plus the entropy of Q of Zj plus constants. So this is, so if for a particular function Zj, this is just a constant. So what we have left here is an it's of course not, right? It's just an entropy. But what we have here is this expression, which we can think of as an unnormalized probability distribution over Zj, which is equal to the expectation of the log joint under all the other approximations. So now if you think for a moment in terms of an algorithm, what we're going to have in the end is some for loop that in each loop goes through all of our Zi's, and when it considers a particular Zj, this object here will be the expectation under all the other approximations, under all the other Q of Zi not j. So if we find an algorithm that sort of inductively always constructs approximations over all the zi's, then whenever we consider one of them, zj, all the other ones will be assigned a distribution. And if we're lucky, we might be able to compute this expected value. Now, of course, we don't know yet whether we're going to be able to do that. We just hope. Right? And now let's just go in and see if this might work. How would we then find a Q of zj which maximizes this expression? So here, we now sort of, instead of trying to compute a gradient, which we can't in function space, we remember that maximizing the elbow amounts to minimizing KL divergence. And here we now have a reduced elbow. We have an elbow over Q of zj. And that means when we maximize this elbow, we're going to be minimizing the KL divergence between Q of zj and this unnormalized, well, now hopefully also normalized probability distribution, implied posterior distribution over zj, which arises from integrating out all the other Q of zi. And that object, right, we know how to minimize the KL divergence. We just set it to 0 by setting this equal to this. So if we have this log p of x and zi, this thing, sorry, zj, this thing, then we can look at this expression, and it might be of a functional form that we can identify as a function of z of j, for which we might know the normalization constant, and then we're done. We have a probability distribution over zj that minimizes the KL divergence, maximizes the elbow, and therefore is the best approximation within this loop. That seems crazy at first. Let me show you an example, and then you'll maybe get the structure. So we'll find an algorithm that iterates repeatedly in a for loop, and inside one iteration of the for loop, it'll iterate over our variables, zi, 1 to n, in each case setting the approximate distribution over zj to this implied posterior distribution, which we get by computing this expected value of the logarithm of p of x and z under all the other zj's. And then looking at the expression and finding hopefully that it happens to be the logarithm of a distribution that we can write down. Why might we be able to write down such a distribution? Well, because we're going to put in some assumptions about what p of x and z actually looks like, right? We're still going to define our generative model for the data for x and z in some nice structured form. For example, we might choose an exponential family. So if this joint distribution over latent variables in data happens to be an exponential family parameterized by some natural parameters, then, as you know, we can write it like this. That's the standard form of an exponential family with sufficient statistics, natural parameters, log partition function. And then the thing that we need to compute, this expected value under our approximations for the logarithm of the joint distribution, log of p of x and z, will be this expression. Right? So now we look where the z's are, right? So the z's don't show up in here. That's just a log normalization constant. Capital Z and lowercase z are different things. So we're left with just an expectation over the sufficient statistics times natural parameters minus log of z. And now we know that we want to set this expression to 0 with respect to the parameters. And that means that we're going to have to set the gradient of the log partition function to this thing, right? So in terms of theta, we're going to have to set it to this. And we know from our lecture on exponential families that this expected value of the sufficient statistics, that this gradient of the log partition function is equal to the expected value of the sufficient statistics under our p of x and z. And that might actually be something we can look up on Wikipedia if it's a known exponential family. And then we have an expression here that we can just plug in there, and then we're done. So here's a summary, and then I'll show you an example. So this so-called free-form variational inference is a framework to construct approximating probability distributions that approximate a posterior p of z given x that might not be analytically tractable. And we do that by iteratively finding minimizers of the KL divergence, or overall finding a minimizer of the KL divergence between the approximation and the true posterior, which we do in an iterative sense by going through subsets of the variables and imposing some factorization. This, by the way, is called the mean field. I actually had this on the slide, but I sort of rushed over it. The reason why it's called the mean field approximation is, again, comes from physics. That's also a little bit why I gave you this physics introduction. Namely, you can think of this factorization as saying there's this system that contains lots and lots and lots of particles. There's too many of them for me to track all of them. And they all interact with each other all the time across time and space. And now what I'm going to do is I'm just going to pretend I'm sitting on one of these particles, Zj, and I want to know what happens to this thing that sits within the system. And I want to see its own distribution. What's the best local distribution for Q of Zj that I can think of? Well, for that, I need to consider the expected value of this overall probability, log of P of x and z, the overall system's energy. Remember that log of P of x, z is the negative energy, under the effect of all the other particles if everyone else in the system also pretends that they are alone. And then the way that they interact with each other is solely through this update step, which you can think of as, well, as we just derived, an expected value of the overall system's energy under everyone's individual contribution. And that is a function of myself, Zj, and that sort of mediation of everyone else on average to me, that's the mean field. Right? The average contribution from everyone else. That's why this is called mean field theory. So in practice, this means we'll define a probability distribution, then we impose a factorization, we do a lot of computations to hopefully find an expected value of the log of P of x and z under all of these approximations, look at it, find that it has an algebraic form that we might be able to track, and if we can do this across all of the variables in our model, then we're done. And then we can just write an algorithm that iterates. So I'll show you now for the rest of the lecture how this works for our Gaussian mixture model in an extension of the Gaussian mixture model. But before I do that, I want to tell you a little bit also why I'm doing this in this lecture. Because every time I bring this up, I realize that what I'm going to do now next is going to seem tedious and complicated and like mentally painful. And that's maybe actually true, but there is a very interesting, very high-level lesson hidden behind that. And what I want you to do now in the next 20-odd minutes is to maybe first keep the following story in mind that I'm telling you really, like, because I think it contains an interesting insight. And it sounds like old men talking about war. So when I did my PhD, I already mentioned this, what I'm going to show you now was really the daily work of machine learning engineers and statisticians. Namely, it was a very manual process. We would write down these graphical models that I'm going to show it to you now, graphical models that look like this. This would happen on a blackboard. You would stand together with your colleagues, write down models, and think a lot about algebraic expressions. And there was a whole lot of theory about these graphical models. This lecture also used to be a lot about these graphical models. There were all sorts of concepts like induced factorizations and induced covariances, explaining away structures, V structures, colliders, and so on. We had words for all of these with the plates and so on. Because the work largely involved writing down math on a piece of paper or a blackboard, then doing the very tedious thing that we are now going to do together, and then finding an algorithm arising from all of this that you then had to implement on a computer. That was very hard to get right. There was usually a lot of bugs, so they were quite hard to fix. And then you had these updates that we're going to see emerging now from the computations that would give an algorithm that actually runs, but once you had it all right, worked really beautifully, and then you could write a cool paper or build some product. And actually also build products. So this is how some early tools for machine learning were actually built, like how online recommender systems were built for large platforms like Xbox Live and so on. That felt like a really tedious process. And it used to be a joke that was like how PhD students would spend their time. And someone actually said, well, why don't we just always use Markov chain Monte Carlo? and there's sort of a running gag that by the time you had implemented this algorithm, your Markov chain Monte Carlo algorithm had converged, and you could have just taken the samples from that. So the value, of course, was in doing the derivations once and then having a very efficient algorithm. And because it was so tedious, very precisely, I think actually because it was so tedious, and you're going to see in a moment how tedious it was, people stopped doing it by the time deep learning arrived. And they got excited about gradient descent and said, how about we just get rid of all of these nasty derivations and just do gradient descent from now on. I'm going to highlight this on Tuesday next week. And interestingly, in doing that, the whole community actually moved to a different type of variational bounds which don't require these nasty derivations, which are just gradient descent. And in doing that, we actually lost the plot for a little bit. It lost some functionality, and I'm going to show you on Tuesday an example, a high-level example of how I think this happened. And actually, none of us really realized, I think, for a while, up until someone discovered that you need the structure again in some deep learning architectures, and it can be very powerful. And that idea was called attention. So I'll try and highlight that story, and I'm telling this to you now, giving this spoiler, because I want you to just keep your attention for 10 minutes as I'm doing these nasty derivations. I realize that they are tedious, but there is a lesson hidden in them if you squint through the math for why people might have stopped doing them. So on Tuesday, I showed you this Gaussian mixture model. Here's our data. Remember the scatter plot with the dots. There's we think that there are clusters in there. We think that they are described by some Gaussian clusters which have a mean and a variance. And each cluster has a weight that is parameterized by some probability distribution, a discrete distribution that is represented by a vector of numbers called pi k that contains numbers from between 0 and 1 that sum to 1. I showed you on Tuesday how we can optimize those parameters, mu, sigma, pi, by inventing these latent variables z and k, which then induce a factorization. Once we know what the z and k's are, then it's easy to optimize for mu and sigma and pi. And then when we have mu and sigma and pi, we can again compute a posterior over z and k. That was called the EM algorithm. So we iterate between computing a posterior over z, optimizing the parameters given that posterior by optimizing the elbow, the expected complete data log likelihood, and then setting again the posterior over z to the resulting posterior if we fix mu, sigma, and pi. We now realize that was a special case of variational inference where we did completely free-form variational inference, basically. We found the optimal approximation to the distribution over z, namely the true posterior if we fix the parameters. Now what we're going to do is to generalize even further to a point where the true posterior is not tractable anymore. So why might you want to do that? Well, one problem that this model has is that we have to say how many clusters there are. We have to say there are k clusters. And we don't know what k is, right? 2, 3, 4, 5, 6, 7, 10, I don't know. You have to look at the data set, and that's difficult to do. I mean, it's easy to do in 2 dimensions, but difficult in 100 dimensions. So what you might want to do as a general concept is a fully Bayesian Gaussian mixture model. This was something that people like Neil Lawrence and Chris Bishop and David Mackay were very interested in around the sort of early 2000s. And they wrote several papers about them, which I forgot to cite here. Maybe I'll do that next Tuesday. So we're going to do a general Bayesian version of this model. What does it mean to be Bayesian? Well, we're just going to replace these parameters, pi, mu, and sigma, with actual variables. We'll say we'll be uncertain about what pi, mu, and sigma are, and compute posteriors over them. And how would we do that? Well, first, let's think about the algebraic aspect. So instead of a p of x and z given mu, sigma, and pi, we're now going to have a joint distribution over p of x over x, z, p, pi, mu, and sigma. By the product rule, we can write that as the likelihood we already know, p of x and z given pi, mu, and sigma. So that's an object we already had in our Gaussian mixture model, times a prior over those 3 parameters, p of pi, mu, and sigma. But we're already going to impose some generative assumptions. We're going to say this factorizes into a prior over pi, a prior over mu given sigma and a prior over sigma. Why might you want to do that? Because you've done a homework exercise about conjugate prior inference in Gaussians, and you know that there is a conjugate prior for Gaussians with unknown mean and variance called the gamma inverse Vishar. And some of you did the homework on this with Bernardo. And we also know what the conjugate prior for a categorical probability distribution is. Does someone know? It's actually on the slide. So categorical distributions are an exponential family, and they have a conjugate prior, and the conjugate prior is the multivariate generalization of the thing I use to infer who is wearing glasses. It's on the slide, so you can just point it out. It's the Dirichlet distribution. So the conjugate prior for a categorical distribution is called the Dirichlet. And it's here, so I've just written it down. So we say, and this is sort of what used to happen in front of a blackboard, right? Someone said, I've drawn this graph. So this is going to be a variable. Oh, we've got mu and sigma. They're going to a Gaussian. Oh, I know what the conjugate prior for a Gaussian with unknown mean and variance is. It's a Gauss inverse Vishar. Looks like this. We're going to put independent priors over every single component with a Vishar distribution over the inverse of the covariance matrix, the precision matrix, and a Gaussian prior over the mean, and then someone knew from memory that you have to do this product form where you have a Vishar prior over the precision, and then a Gaussian prior given the precision. That's how you get a conjugate prior. And then pi is a probability distribution, so everyone knows what the conjugate prior for a categorical probability distribution is. It's a Dirichlet distribution, which has this particular form. That's a Dirichlet distribution. And those things have parameters, right? They are themselves exponential families because the conjugate priors to an exponential family are themselves exponential families. They have parameters. They're called alpha for the Dirichlet, it's a vector of numbers, and W, which is a symmetric positive definite matrix for the Vishar, and mu, which is a count variable. You know, you might remember that conjugate priors have these count variables, and M and beta for this Gauss inverse Vishar. And you just happen to know that if you lived in that time. And now we realize, okay, that posterior over pi, mu, and sigma is not going to be tractable. Actually, we used to be able to read this off a graph. And if you would have taken this class like 4 years ago, you would now be able to read it off the graph as well, because you can see that there's a collider structure here coming in, all these arrows pointing in. This is a variable. It's an observable. We've seen this. So therefore, all of these things become dependent on each other in the graph, and we cannot expect to find a joint posterior over them. You don't know this anymore because I didn't do 3 lectures on graphical models and instead talked about deep learning and Laplace approximations, but you know, I can tell you that that's something you would be able to read off if you are an expert in graphical models. So now what people used to do is to say, oh, we're going to build a variational bound. And we're going to do a free-form variational bound. So the only thing we're going to do is we're going to impose some factorization over this joint distribution over these 4 things. And the factorization we probably want to have is that the parameters of what used to be our Gaussian mixture model will be one set of variables, and these cluster labels, these Z and Ks, those will be the other variable. Why? Well, because that's how EM works, right? It was somehow very useful to have this distribution over Z. So our approximation that we're going to impose is that whatever our approximation to the posterior over Z, pi, mu, and sigma will be, it will have to factorize like this. There'll have to be one distribution for who belongs to which cluster, and then one distribution for all the variables. That's it. That's the only constraint we're going to put in. And that seems like a very weak thing to do, right? Just one little dot between the distributions. And now we do variational inference, and this variational inference with this really like cranking a big squeaking handle on a big cog. So you sit down with a piece of paper, sometimes it was like an A3 piece of paper in like landscape mode, and then you start with the derivation. You say, what was the rule to derive a variational bound? Well, we will need, under this mean field assumption, this factorization, we will need to compute to find this object, we will need to compute the expected value of the joint distribution, the log joint, under all the other variables in our distribution. So if we want to find the approximation to z, then we need to take an expected value of the log joint with respect to pi, mu, and sigma. And then afterwards, hopefully, we might be able to get a distribution on pi, mu, and sigma by taking an expectation over the same thing under this distribution over z that we've now just found. And then we can iterate. So actually, it might be a good idea to start with z. Why? Well, because the z's are binary variables, right? So we're going to clearly, because they're just a set of binary variables, we will learn probabilities for them. I mean, the most general distribution over a finite set of binary variables is a probability distribution, a discrete distribution that just contains numbers. Okay? So let's do those first. So our goal is going to be, let's compute an expected value under whatever the other distributions are. We don't know yet what they are, over this log joint. And now we look at the expression for the log joint. So we go back up again, we look at it. Okay, this is the thing we need to plug in. Right? That's the object. And these have actually forms, right? So P of pi is the Dirichlet, P of mu and sigma is this thing down here, which has this factorization structure inside. And this thing, P of x and z given pi, mu, and sigma, well, it's up there, this thing. We're just going to plug that in with a logarithm in front. So now we find that this, when we plug this in, we'll get one term over P of z given pi. Clearly, this only contains pi. There is no mu and sigma. So our expectation over pi, mu, and sigma actually already simplifies. It's just going to be an expectation over pi. And then there's a term over P of x given z, mu, and sigma. So that contains no pi, only mu and sigma. So that will simplify the computation as well. We'll only need to take an expected value over mu and sigma. And then, if you go one slide back, there's a lot of terms here in the back that don't actually depend on z at all. So we just can forget about them. Right? So they won't contribute to our approximation to Q of z. So those are the two terms that we need to compute. And now we plug them in. So what was P of z given pi? Well, it was actually happened to be a product over the individual zn, and then a product over the individual component k, times pi k raised to the znth power. So if you take the logarithm, we get a sums over n and k, z and k, expectation of log of pi k. So if you take the expectation under this joint distribution over pi, mu, and sigma, well, mu and sigma don't matter, and pi is the only thing left, and it goes through all of these sums and past the z and k, and we're just left with an expectation over log of pi k under whatever our approximating distribution on pi will be. We don't know yet what that is, but we know now that we will need to be able to compute the expectation of log of pi k under this distribution. Okay, let's go to the second term. We just write this in, we leave it like this. Now we go to the second term. Here we need to take an expected value over the log of P of x given z. So on the previous slide, we had log of x, we can actually, if we know z, right, then we know what log of P of x given z is. It's just a product over the individual xn over Gaussians, and specifically the Gaussians from cluster K indicated to us by z and k. So we go through a sum over both the n and the k, if we want to do, if we need the logarithm, right, all the products turn into sums, over z and k, which are these 0, 1 variables that tell us which cluster we are in. They basically select an entry in the sum over k. And then once we know which term in the sum we select, we just have to write down the logarithm of a Gaussian. So that's this, right? So Gaussians are exponentials of minus quadratic form with mean and covariance, and then there's the log normalization constant that contains sigma. We need to take the expected value over this thing under whatever our approximation to mu and sigma is, which we don't know yet, but that's the thing we're going to need to compute. So now we know something we'll need to compute. And now we do this cool variational inference trick, and we say, what do we actually have here as a function of z? So this expression here, this will be, up to normalization, the logarithm of our distribution over z. And that's a function of z. And we see that what this is, well, it's a sum over n and k. That means there'll be a product in our probability distribution. that factorizes over all the n, over all the individual samples. And then there'll be a z and k and some number that we have to compute. We don't know yet what that number is. It'll have to be computed from our approximations over q of distributions over pi and mu and sigma, but it's just going to be a number. So let's give a name to that number. Let's call it the logarithm of rho nk. This is a real number, so it can be the logarithm of something. And then what we have here, if we stare at this and like squint with our eyes and think of it as a distribution over z, we can take the exponential and we see that what we're going to get is a product over every individual datum, all the individual components, all the clusters, times the number rho nk raised to the z nk power. That's not just a discrete distribution, it's a factorizing discrete distribution. Aha! And now the only thing we need to make sure is that it's actually a distribution, so that means the rho nk have to sum to 1. And we can do that through the normalization. So by using this constant over here, which we haven't used for anything yet, to normalize and set the actual parameters of our distribution to R and K, the responsibilities from EM, which are now going to be equal to rho nk divided by, well, the rho-wise sum of the rho nk. So that's a dot sum axis equal to 1, basically, operation, which will then give us our approximating distribution to q of z, the posterior over z, which is a fully factorizing probability distribution, categorical distribution over the z nks, parameterized by a responsibility R nk. Aha! So what's just happened is we started by assuming that there will be some approximating distribution over the z's and one over the pi, mu, and sigma. And what the variational inference has automatically told us, without us imposing it, is that this bound actually factorizes over all the n. Every single x will have its own z n, which contains k entries. And they'll be independent of each other. We didn't impose this, it just happened because our model has this structure. This is called induced factorization. And now we know that this is a discrete distribution. Discrete distributions are very easy to work with. The expected value of a discrete distribution, the expected value of the random variable under a discrete distribution is just the probability for, like that's in the vector, right? So the expected frequency with which you're going to see cluster k for sample number n is literally just R and K. It's just a property of discrete distributions. Here it is, so discrete distributions. And now you could go to like the Wikipedia page for discrete distributions and read up all the properties of it. Like it's, for example, that it's independent between the ZKJ and it's like, you know, like everything is here. Okay. No, but so far we only have an approximating distribution for the Z. We need to be able to build it, we need an approximating distribution to pi, mu, and sigma. And then we need to be able to evaluate this thing, this expected value of this nasty expression here. So now let's turn our attention to pi, mu, and sigma and see if we can find approximations for these, now knowing that our approximating distribution to z will be a fully factorizing categorical distribution. Okay, here I'm going to spare you some nasty computation, and I'm just going to say, I'm going to motivate some convenient notation. I'm going to introduce this nk, which are the column-wise sums over the responsibilities. It's basically the expected number of data points in each cluster. We're going to compute a weighted cluster mean, weighted by the responsibilities. And we're also going to compute a weighted empirical estimate for the covariance in each cluster. We call that sk. That's just a convenient thing to have, because otherwise the slide becomes so big that I can't use normal font size anymore. And now we're going to try and identify our approximating distribution over pi, mu, and sigma. Remember that we made no further assumptions. We just said that there will have to be a distribution over pi, mu, and sigma. And the way to find that is to find its logarithm, actually, is to compute the expected value of the log joint under q of z. That's our operational rule for variational inference. So let's go back again a few slides, write down the log joint. Here it is. I've just copied it over from the previous slide. We will need to take the expected value of this thing under our categorical distribution over Q, over Z. Now we look at this expression, and again we see, okay, this stuff does not depend on Z. There's no Z in here, so that's going to be easy. We just leave it in there. It's still, I mean, it's a function of pi and mu and k, so we'll need to keep it under consideration. We can't call it a constant, but we don't need to take an expected value over Q of Z because Z doesn't show up here. Z shows up here and there. Okay, so let's move the expected value inside and then rearrange some terms, because we also see that there is a pi here, but not here, and not there, but there's a pi here. And there's a mu and sigma here, but not here and there, and it's a mu and sigma here and there. So let's rearrange the sum. Let's move this bit over here and this bit over there. Now we're going to have a term that a bunch of terms that depend on pi. One of them only depends on pi, on nothing else. One of them contains Z, so we need to take an expected value over Z under our approximation, which we now have. And then there'll be all the terms that depend on mu. One of them does not depend on mu. One of them depends. One of them does not depend on Z. One of them depends on Z. So let's take an expected value over Z in here, but Z actually just shows up linearly in here in a big sum. So to take the expected value over Z and K, we literally just replace this with our R and K, our responsibility that we just found. Okay, so I've just copied over this expression from above. It's the exact same line again. And what we now see is, if we stare at this, oh, hang on, there is something over pi here, and then there is a sum over the K and a sum over the N. So this sum over K shows up both here and there, so we can take it outside. And in this Q of Z, we have a factorization over the N's and the K's as well. So let's plug all those sums in. We do that here. And we will get, I've just rearranged terms. Let's actually do one after the other. Let's first do the one on pi. So just this term, let's just think about it. This will be a distribution over pi. Let's write this down. So it's the logarithm of a distribution over pi. So it's this term, which just contains pi. That's our Dirichlet prior, log Dirichlet prior, plus an expected value of under the discrete distribution over log of p of z given pi. Remember, what is p of z given pi? Well, it's just, so the logarithm of p of z nk given pi is just pi k. So let's plug that in here. And now we have from the Dirichlet prior this term, from this term this. Well, we can rearrange the sums. You can put, there's a sum over k everywhere, so we put it outside. There's one sum over n left. The log of pi shows up everywhere, here and there, so we can take it outside of brackets. And our log probability distribution over pi will be a sum over k times a bunch of numbers. So that means as a distribution over pi, we have to take the exponential. Our distribution will be a product over k, pi k raised to some power up to normalization. And if you've paid attention in the exponential family lecture, you know that that's a Dirichlet distribution. That's the exact form of a Dirichlet distribution. So without imposing, without requiring that our algorithm uses a Dirichlet distribution, it turns out that our approximating distribution is a Dirichlet, just from the factorization assumption. The algebraic form emerges naturally. We'll have a Dirichlet approximation which contains parameters, so numbers, alpha plus nk, where the nk are these things. It's just a name for them. And then, so you can look up on Wikipedia everything about Dirichlet distributions. And on Wikipedia, you can click on this link. You'll find lots and lots of properties of Dirichlet distributions. In particular, you'll find something about the expected value under a Dirichlet distribution of the log of pi. Ooh, and this is where the loop closes. So now we go back and we said, well, our problem was initially that to compute our expected value over, so to compute our probability distribution over z, our approximation, we would need an expected value over the logarithm of pi of k under whatever our approximation on pi was. So now we know our approximation on pi will be a Dirichlet, and we know that this expected value of the logarithm of pi under a Dirichlet distribution happens to be something we can implement. It's this nasty thing. It's called the di-gamma function, and it's available in SciPy. So now we're going to be able to write a piece of code that does the first step to compute the approximation to Q of z. And now we need to do actually the same thing again for mu and k. So I'm not going to do this in detail here, right? So this is the stuff from before. I've copied it over again. Let's now focus on mu and sigma. Let's find the approximating distributions for mu and sigma. Well, here we discover that there's a lot of sums, and here again, so everything will become a product over independent distributions over mu k and sigma k. So there's again an induced factorization. And if you do the math, it's basically the same as for the Dirichlet. You find that there is a very tedious, long expression that tells us what the functional form of the distribution over mu and sigma will be. It'll factorize over the clusters k, and the individual distributions happen to be a product of Gauss inverse gammas. So they are, again, conjugate posteriors. And then you can go on Wikipedia and look up, see if you can find, so here's the last slide, whether we can find the terms we need to compute, to close the loop, to close the inductive loop, and find the terms that we need to construct our approximation on the posterior on z, Q of z. So for that, from the previous slide, we know that we need to be able to compute expected values of log of pi. We know how to do that. It's a Dirichlet. And then we also need expected values of the log inverse determinant and a quadratic form. And for that, back in the day, people had big books. For example, there were a set of cool notes by someone called Sam Roweiss that you could read up on, and they would, or you would go to your colleague down the corridor, Tom Minka, someone like that, and they would tell you, I know how to compute the expected values of quadratic forms under Gaussian. There are these nasty expressions, here they are, you can read them up and you just implement them. And they involve functions that we know. They're nasty expressions, but they're functions that we know. So that means we can now do an update loop that initializes a Dirichlet distribution for pi, a Gauss inverse gamma distribution for mu and sigma, and a categorical distribution for z's at random. And then it iteratively updates. It first constructs a new approximation for the categorical distribution over z and k by computing these numbers, which are proportional to this object, which we have read off from the previous slides. And these are all variables that we have because they are parameters of the approximating distributions for mu and sigma and pi, for the Dirichlet and this Gauss inverse gamma. And then we do the update that was on the previous slide to compute conjugate posteriors given the z's for pi, mu, and sigma. And we keep doing that. If you want to see how this works, I actually uploaded the code to beat up Jupyter Hub, but it's so long that it doesn't make sense to look at it now. Instead, I can show you as a concluding picture how this algorithm works. So here is our data set again in black dots. This old faithful Geyser data set. And now what I've done is I've initialized this what's called a Dirichlet Gaussian mixture model or Bayesian Gaussian mixture model with 9 clusters. I said, like, just try 9 clusters, see what happens. And this is the initial configuration. That's the expected load of each cluster. It's a draw from a sparse Dirichlet distribution. And those are the initial clusters. In alpha value, you see their weight. So the faint ones are very low weight, and the thick ones are high weight. And there are 9 of them. They're randomly initialized. And now I just run the algorithm for a few steps. Every time it updates the r's and then the parameters of the conjugate posterior to mu, pi, and sigma. And what this algorithm is now able to do is it discovers that there are just two clusters. And back then, people were super excited about this. You learn how many things there are in a data set. Isn't that a cool thing to be able to do? You show the algorithm the world, and it decides for itself how many things are in your world. In this case, 2. And also what they look like. Namely, they have 2 means and 2 covariances. So this framework, called variational inference, is maybe it's a more civilized weapon from a more civilized age. It used to be the way that we built machine learning, but this is actually what we used to call machine learning, building these very structured algorithms that required a lot of tedious work. In this case, you first write down your generative model, P. Then you decide you're going to do variational inference. You impose a factorization on your approximating distribution over the unknown latent variables. In the case of the Gaussian mixture model, they are z, pi, mu, and sigma. Then you go through the math on a piece of paper, or on a slide, and derive the variational updates. You find some forms that you know how to compute. It involves lots of known integrals, lots of, oh, I know how to compute this under an exponential family. I know how to compute that expected value. And then you implement this as an iterative loop that keeps doing these updates. In fact, you can even evaluate the variational bound, the elbow, as you do, and you can see the elbow rise. That used to be a bug-fixing test people did. Just compute the elbow and see whether it actually goes up. If it doesn't go up, you made a mistake. And that used to be very tedious. It was very difficult to automate. It required a lot of knowledge and finger, feeling and elbow grease, like the ability to sit down for several hours to do the derivations. And it's what used to be a lot of work for research engineers. And on Tuesday, I will briefly tell you the thing that you probably expect, that people stopped doing this because autodiff was cool. And then we'll rediscover that in doing that, we actually lost a bit of structure, namely this induced factorization idea that really helps with algorithmic efficiency. And it was rediscovered, arguably, that's going to be my point, by some people in the deep learning community in the form of attention. So with that, please give feedback. I'll see you on Tuesday for the last content lecture of term, and then afterwards there'll just be a summary. Thank you very much.